Welcome. This is our group's final presentation on a project titled Predicting Survival on the Titanic. In 1912, the Titanic was set for launch. The trip was planned to start at Southampton and sail to New York City, but unfortunately that was not the outcome for more than 2,000 people on board. The Titanic had really high expectations and it was described as unsinkable, but contrary to all predictions, the Titanic started to have technical difficulties immediately after it sailed. They were not alarming, but they made the captain cruise at maximum speed, which unluckily led the Titanic to collide with an iceberg and completely sink, taking more than 1,500 lives with it. However, many people survived, and we believe it was not a matter of pure luck. Aside from randomness, such as the locations of individuals at the time of the catastrophe and whatever they were doing, there are key factors that played a role in the destiny of each person on board. On this project, we solved the least squares classification problem and used logistic regression to build a model that predicts if a passenger on the Titanic survives, taking into account their age, gender, economic background, and their place of embarkation. This will all be better explained as the presentation continues, but for now, we move on to our goals.
So our goals for this project were to implement a least squares classification problem in a real life scenario. We wanted to do it through a model that wasn't fully explained in class, which is logistic regression, just so that we could learn a little bit more as we finished this project and ended off this semester. And the final goal was really to make it super understandable for anybody who might look at it. So whether they're technical background or not, they could look at this problem or this project and take something away from it.
And now a little more explanation on the project details. So we were given information through a website called Kaggle about the passengers on the Titanic, and we're trying to predict whether or not they survived the wreck. Some of these features about the passengers include the name, age, gender, passenger ID, number of siblings aboard, number of parents and children aboard, their fare, their cabin, and port of embarkation. And the passenger label we were also given for the data set is if they survived or not.
Moving on to my contribution to the project, we have a file called load.py, which basically starts and sets up the data in a way that can be later modeled. This is done by performing feature engineering on the initial table, which included attributes that were not usable mathematically, such as categorical data like names, sex, or embarkation place. Specifically, I started by removing the name and ticket columns completely, as I felt it didn't add any value to the purpose. And then I removed each row that had empty cells, because the model would take them as zeros and it would return in misleading information. Lastly, I performed conversions on the remaining categorical attributes to one-hot vectors, such as the embarkation place, sex, and economical class. The way one-hot vectors work is that the attribute is basically split into two or three, whatever needed. And if the individual is a male, then the male is going to have a 1, and the female is going to have a 0. That's the same case for economical class in place of embarking, but the only difference is that the latter two is not two variables, but three. For example, for the place of embarking, we have Cherbourg, Queenstown, Southampton, and for the economical class, we have upper, middle, and lower classes. And when one is at the 1, the rest are zeros. To finalize, I split the resulting data set into two different sets randomly, but I put 80% of the set into a training set and the remaining 20% into a testing set, because otherwise we'd be testing on the same data that we're modeling, which would return results that seem correct but really aren't because of bias.
So for my contribution, I took the 80% of data that Diego had split up, and I used the sklearn library to fit it into two different models. The first one we used was a normal equation model, and that didn't give us very accurate results. The main reason is because normal equation doesn't, it's not ideal for situations where you need a yes or no answer, so to speak. So the second model we used was logistic regression, which did give us a very accurate result. because logistic regression is really useful in cases where you do need an absolute answer, a 1 or 0, so to speak. In this case, survived or not survived. So that was the main focus of the train.py file.
And now moving on to my contribution to the project, I created the evaluate.py file, where I evaluated the models created from train.py and used the test set created in the beginning, the 20% test set, and graded the accuracy of each model. And the normal equations model seemingly performed okay with a 60% accuracy, but I'll explain why this was really bad and it did not perform well in the next slide. The logistic regression model resulted in an almost 80% accuracy, which far outperformed the normal equations method. And these are the confusion matrices for both logistic regression and normal equations method. And as you can see on the normal equations method, the predicted label, meaning whether they survived or not, 1 being they survived, 0 being they didn't. The normal equations method predicted that every single person did not survive, which got us a 60% accuracy, but is not very ideal for classification, as it only classifies it as 1. Whereas the logistic regression model um, predicts it fairly accurately with a very good true positive rate and true negative rate. And I'll move on to the ROC curve, which models the true positive rate against the false positive rate of the logistics regression curve. Meaning you want to try to increase your true positive rate without increasing your false positive rate by adjusting the threshold. And this shows an ideal threshold is probably somewhere around here where it maximizes true positive rate and minimizes the false positive rate.
And the learning outcomes of this project, it was a lot for us, but we just tried to focus on 3 here. The first one was feature engineering. It's super essential for an accurate machine learning model. And we all kind of learned just how much this is used in machine learning in general. It's helpful to manipulate the data in a way that makes your machine learning algorithm much more accurate. The second thing that was really great for us to learn more on was logistic regression. It helped us see just how it's better suited for classification problems such as this one. And so we got to see a lot of its benefits and some of the places where normal equations fall short. And then the last thing we learned a lot about, as Eric just described, was confusion matrices and ROC curves. And those were just some really simple ways of understanding data better and getting visual cues as to make sense of all the work we put in.
And
Thank
that does it for our presentation. Thank you.